Hello everyone. So our today's topic is pointers and dynamic arrays. These are two fundamental concepts in programming. So let's start with pointers. So a pointer is a variable that holds the memory address of another variable rather than storing a value directly. It stores the location in memory where the value is found. This is incredibly powerful because it allows for more flexibility in how we manage memory in our programs. Think of a pointer like a signpost that directs you to the actual data rather than being the data itself. So this capability is especially important when we deal with large data structures, memory management, or functions that need to alter values outside their own scope. So for example, in C or C++, if we declare integer star p, this p is not holding an integer value, but rather it holds the address of some integer variable in memory. So you can see the basic structure for declaring a pointer and allocating memory for a new object in this slide. So here if you see inv underscore item star p item, this line declares a pointer named p item of type inv underscore item. The star indicates that p item is a pointer, meaning it will store the memory address of an inv underscore item object, not the object itself. Next line we have p item equal to new inv underscore item. So this line is crucial because it allocates memory dynamically for an inv underscore item object using the new operator. The new operator allocates memory for an object and returns its address. This address is then assigned to the p item pointer. By doing this, p item now holds the memory address where the new inv item object is stored. Finally, we can combine these two steps in one line of code. inv item star p item equal to new inv item. This line both declares the pointer and assigns it the address of a newly allocated inv item object. This method is more concise and is typically the preferred way to both declare and initialize a pointer. A few important things to keep in mind when working with pointers and dynamically allocated memory. Always ensure that dynamically allocated memory is properly freed to avoid memory leaks. Pointers that are left uninitialized can cause undefined behavior. So on this slide, here's how we might explain this slide about an easy error to make when working with pointers. Now let's look at a common error that many people make when using pointers and member access. The difference between these two expressions can be subtle, but understanding it is crucial to avoiding errors. So here if you see star p dot member, this expression dereferences the pointer p and accesses the member of the object that p points to. The star p gives you the object stored at the memory address that p holds. Then the dot operator is used to access the member of that object. This is the correct way to access the member of an object when you are working with pointers. Essentially, we're saying go to the address stored in P and get the member of the object there. Now, start P.member. What that mean? Here the error lies in the order of operations. So what this expression does, it is first access the member of the pointer p itself. W- so basically, which doesn't make any sense unless p is an object with a member, and then it dereferences whatever is stored at that memory location. In most cases, this is not what you mean. Instead of dereferencing the pointer and accessing the members, this form can lead to unexpected behavior or even runtime errors if you accidentally try to dereference an invalid memory location. So a good way to avoid this kind of mistake is to use the arrow operator when so we'll see it on the next slide also. Here, this arrow operator. So this operator is a piece of syntax sugar, meaning it simplifies the syntax for accessing members of an object through a pointer. Instead of needing to explicitly dereference the pointer and then access a member, we can use this to perform both steps in one go. So here how it works. In the first line of code, inv underscore item star p item, we declare a pointer p item, then p item that can hold the address of an object of type inv underscore item. Now on the second line, we allocate memory for a new inv item object. This allocates memory and assigns the address of this newly created inv item object to the p item pointer. Now we get to the actual member access. P item cinv set inv 5. This statement uses the arrow operator to dereference p item, meaning it accesses the object that p item points to, then calls the set inv function to set the inventory to 5. This is the simplified form compared to the more verbose version, which is star p item dot set inv 4. So here we explicitly dereference p item using the star operator and then access the set inv member function with the dot operator. While this works the same way, it's a bit more cumbersome to write and read. So the arrow operator is cleaner and more concise. It's widely used in object-oriented programming with pointers because it makes the code more readable, especially when working with classes and structures. So you can just keep that mind that the arrow operator is equivalent to dereferencing a pointer and accessing a member, but does so in a more elegant and readable manner. This should clarify the use of the arrow operator versus the more explicit pointer dereferencing. inv equal to myq. It is equivalent to this formula, this expression, which is the correct way, or either we can use this one. This one also works well, but it's more verbose. The arrow operator is usually preferred because it's more readable and concise. Now moving forward to the overloading the assignment operator. So when we overload the assignment operator, we typically return the object that called the operator, and to do that we use the this operator. Here's why, you will see. When we write a custom implementation of the assignment, of the assignment operator, we want to allow for chaining of assignments. So chaining will look like something. If you see here on this slide, overloading the header, so the return type is INV item, and which means the function returns a reference or to an INV item object. This is important because returning a reference allow us to support chaining of assignments, as we saw in the previous example. Now if you see, returning the calling object, this one, then this one is the member function. So this this is the member function of the class INV item. Then we have this dot operator specified that the operator equal is a function belonging to the INV item class. Now this one is the operator keyword, and so this part of the function header is what we call the operator keyword. This keyword is used in C++ to specify that we are overloading a particular operator. In this case, we are overloading the assignment operator. Equal sign is the assignment operator. So why do we need the operator keyword? This keyword allows us to define custom behavior for built-in operators when they are used with objects of user-defined types. So by overloading operators, we can make our classes behave more like built-in types. So here, next we'll see here, this is the assignment operator. Then here, if you focus on the right hand side operation function and this one, you will have operand on the right hand side of the equal operator, constant reference, save member but no modification. So that means if we break down the whole thing, first of all we have constant INV item, and the right hand side operand is passed as a constant reference. This means that we are not making a copy of RT_side, which saves memory and processing time, but we also ensure that RT_side cannot be modified inside the function. The constant keyword ensures that the data members of RT_side are protected from being changed during the assignment operation. So if we pass the RT_side object by value, it would create a copy of the object. This could be inefficient, especially if INV item is a large object with many members. So by passing it as a reference using the AND symbol, we avoid copying and instead of work directly with the original object. And item 2, in this expression we have item 1 is the left hand operand. Since we want item 1 to receive the value from item 2, we need to modify item 1. This is why the left hand operand is not constant. We need to change it to reflect the assignment. So this is the body. Here we are assigning the value of the INV member from RT_side to the INV member of the current object. Essentially, this is where the actual assignment happens. we are copying the data from the right hand side, RT side, to the left hand side, the calling object. In this case, we are assuming that INV is a member variable of the INV item class, and we are copying its value from one object to another. And then we have returned start this. After completing the assignment, we return this. This refers to the current object, the left hand side of the assignment. By returning this, we enable chaining of assignment operation. For example, like item 1 equal to item 2 equal to item 3, as we saw before. Now here, if we focus more inside the body, this first line is storing the new data. So this line assigns the value of INV from the right hand operand to the INV member of the calling object. So we are storing the new data in the current object by copying it from the right hand side of the assignment. So this is how it works. Then returning the calling object. So as I just said earlier, this is just returning the calling object. It should be in the same slide. Anyway, so the syntax. So syntax is like, if you look at this slide, it is very straightforward to define as destructor. It will always have the same name as the class, but are prefixed with a tilde, or like this symbol tilde. So here, this is the declaration of the destructor for the class INV item. It has no return type and takes no parameters. So the destructor is called automatically when an object goes out of scope or it's explicitly deleted. Here, inside the destructor, we have two lines: delete my pointer, delete my dynamic array. So first one deallocates the memory that was allocated dynamically for my pointer. If you use new to allocate memory for a pointer, you must use delete to free the memory when the object is no longer needed. If you forget to do this, your program could have memory leaks where memory is never released. Now the second line, similarly, this line also frees memory for a dynamically allocated array. The this parenthesis after delete tells the compiler that we are deleting the array, not just a single object. So it's important to use delete and then this parenthesis when deallocating arrays. Otherwise, only the first element might be freed, leaving the rest of the memory allocated. So here we will now learn about copy constructor. So it is a special constructor in C++ which is used to create a new object as a copy of an existing object. So the copy constructor takes a single parameter that is a reference to an object of the same class. So for example, in a class INV item, the copy constructor would look like INV item, and then inside the parenthesis constant INV item and other. So it must be a call by reference parameter. because passing by value would invoke the copy constructor itself, leading to infinite recursion. So additionally, it's typically a constant by reference. This is to prevent modification of the original object while still allowing access to its data. Now, a copy constructor creates a deep copy of the object. This means that it copies not only the object's data but also any dynamically allocated memory, creating an entirely independent object with its own resources. Now, so a deep copy allocates new memory and copies the contents of the original object into that memory. This ensures that changes to the new object don't affect the original object and vice versa. In contrast, a shallow copy merely copies the pointer addresses, so both objects end up pointing to the same memory. This can cause issues like double deletion when one object is deleted, as it invalidates the pointer for both objects. Now let's take a look on the shallow copy. What happens in a shallow copy? So here in this example, so we can say a shallow copy just copies the values from one object to another without worrying about dynamically allocated memory or pointers. In this code, we are simply assigning the INV member of the RT_side object to the INV member of the current object. This works fine for simple data types like integers or basic data members that don't involve dynamic memory allocation. So it is perfectly fine when your class does not use dynamic memory. For example, if in INV is an integer or a basic type, this shallow copy will work without issues. But if your class uses pointers or dynamically allocated memory, a shallow copy can lead to problems. Both objects would end up pointing to the same memory location. So which means if you change to one object, that will affect the other, and deleting one object could invalidate the pointer in the other. So if your class manages resources like dynamically allocated memory, shallow copies can result in double deletions or memory corruption. If INV were a pointer, both the current object and RT_side would share the same memory address after the shallow copy. When one object is destroyed, its destructor would free that memory. It will leave the other object with a dangling pointer. So in this case, where your class uses dynamic memory, you need to implement a deep copy where you allocate new memory for the copied object and copy the contents instead of just copying the pointer. So just a shallow copy because I'm just assigning values. Fine, unless the class uses dynamic storage. Okay, so here we will see a copy constructor syntax. In this code, let's break it down. First, inventory, a constant inventory, and my copy. This is the constructor declaration. The copy constructor takes a single parameter, my copy, which is a constant reference to another inventory object. The use of constant ensures that the original object, my copy, is not modified and the reference avoids unnecessary copying. Now in the body of this constructor, we have shelf space equal to my copy dot shelf space. So and then the second line is in stock equal to my copy dot in stock. So these are simple member variables, likely integers, so a shallow copy is fine for them. These are basic data members. Um, Now allocating new memory for dynamic members, you can use this line is for that. Inv list equal to new inv item, shelf space. Now here inv list is a dynamically allocated array, so we create a new array with the same size as my copy dot shelf space. This ensures that the new object this has its own separate memory, avoiding shallow copying. Copying the contents of the array. Now, after allocating the memory for in INV list, we need to copy the actual contents from my copy.inv list. So, this is the for loop is for. This for loop iterates over each element of the INV list array and copies the contents from the corresponding elements in my copy.inv list. Without this deep copy, the default shallow copy would just copy the pointer, meaning both objects would share the same memory for INV list. This could lead to issues like memory corruption or double deletion. So by implementing this copy constructor, we ensure that each inventory object has its own independent copy of the data, including dynamically allocated memory. So here, like any other constructor, this is the constructor. This is passed by reference, constant reference in this case. Shallow copy of the part that isn't using dynamic memory. Deep copy requires creating new memory storage for dynamic items, then storing the original values in the new memory locations. So the big three, we have looked at these three things like copy constructor, assignment operator, and destructors. So these are called the big three. So here the big three are important when working with classes that involve dynamic memory allocation or other resources that need explicit management. These three functions, as I said, copy constructor, assignment operator, and destructor. As we saw before in our previous slides, the copy constructor, I'll just go through again just to make sure you have a better understanding on these three. So the copy constructor creates a new object as a copy of an existing object. If your class uses dynamically allocated memory or other resources, you need to ensure that each object manages its own memory rather than sharing it with another object. Then second, assignment operator. So this allows you to assign one object to another. When you overload this operator, you ensure that your class performs deep copies when necessary, rather than just copying memory addresses. And lastly, you have destructor, which is used to free any resources that an object holds when it is destroyed. For classes with dynamically allocated memory, the destructor ensures that the memory is properly released, preventing memory leaks. Now, when you need all three, so firstly, if your class uses dynamic memory storage, then you will need to implement all three of these: the copy constructor, assignment operator, and destructor. However, if your class doesn't involve dynamic memory or resource management, the default versions provided by C++ are often sufficient. So you don't have to write or include any of these, because the C++ compiler already have its default version of all three. So either you need all three or you don't need any of them. This is a common saying because if your class manages resources, failing to implement any of those could result in memory leaks, double deletions, or other issues. So now we will learn about dynamic arrays. So dynamic arrays, it provide flexibility compared to standard arrays in terms of size and memory allocation. First of all, in C++, array variables are constant pointer variables. It means once you declare an array, it points to a specific memory address, and this address cannot be changed. This applies to both standard and dynamic arrays, but the key difference is how and when the size of the array is determined. Well, a standard array has a fixed size which must be determined at the time of compilation. For example, integer array 5. You can just declare the size, the standard array of size 5. You can write it like that. But once you declare, you cannot change the size of this array during runtime. The size is known and fixed at compile time. On the other hand, dynamic array does not have a fixed size at the time of compilation. Instead, its size is determined while the program is running, which gives more flexibility, especially when you don't know how much memory you will need in advance. So dynamic arrays are created using pointers and memory allocation functions like integer star array equal to. So we'll see more example on our next slide. Because this allows you to create arrays with sizes that depend on user input or other runtime conditions, which makes your program more adaptable. Well, it is particularly useful when working with data structures that need to grow or shrink in size, such as vectors or lists, or when handling input where the amount of data is not known ahead of time. So if you remember, we learned about vectors on our previous lecture. However, managing dynamic array memory requires careful attention, including releasing the memory when you are done with the array to avoid memory leaks. At the end, we can say the primary difference between standard and dynamic arrays is when the size is determined at compile time for standard arrays and runtime for dynamic arrays. Okay, so here we'll see array variables, which are essentially pointer variables that refer to the first element of the array. So, well, arrays are stored sequentially in memory. This means that each element of the array is placed next to the other in consecutive memory locations. So for example, if you declare an array integer is A10, the elements of this array will be placed in memory one after the other. The name of the array, like A in this example, refers to the first element of the array, which is why we say that an array variable is a type of pointer variable. Now in this example, both A and P can be thought of as pointers. A is a constant pointer to the first element of the array, meaning you cannot change A to point to a different memory location. Well, however, P is a regular pointer variable that can point to any integer value in memory. You can change the memory address P to points to. So, understanding that array variables are pointers helps explain how arrays are passed to functions. When you pass an array to a function, you are actually passing a pointer to the first element of the array. This is why you don't need to specify the size of the array in the function parameter. So we'll see more details here. So now we'll see what is the relationship between array variables and pointer variables. We'll see more example here in details. So a and p are not a and p are pointer variables in this example. If you see integer a 10, type diff, integer star, integer ptr, integer ptrp. Now a is the name of an array, which, as we have discussed in our previous slide, which is a constant pointer to the first element of the array. Now p, on the other hand, is a regular pointer of type integer ptr, which is an alias of integer star. Now if we write p equal to a, which is legal, you're telling p to point to the same location that a points to, so we are telling p to point to the same location that a points to, which is the memory address of the first element of a. This is perfectly legal because p is allowed to point to any integer and a is pointing to the first integer in the array. Now after this assignment, p now points to the first element of a, just like a itself. Then next, a equal to p, which is illegal. Why? The reverse assignment is like a equal to p is illegal because a is a constant pointer. You cannot change where a points. Once an array is declared, its name, like a here in this case, it always refers to the same memory location, the starting address of the array. This is why trying to assign a new pointer to a results in a compile time error. So understanding the difference between a constant pointer like a and a regular pointer like p is critical when working with arrays and pointers in C++. It helps explain why arrays are passed by reference to functions, and clarifies how memory is managed and when dealing with dynamic arrays. Well, so this slide is already almost saying the same thing I just said on our previous slide. So like, it's more than a pointer variable, constant integer pointer, array was allocated in memory already, variable a must point there always, cannot be changed. So these are the things we already discussed. And here this is also saying the same thing we just saw about dynamic arrays. So like standard arrays has some limitation, but dynamic arrays can grow and shrink as needed, because if you don't use the size of the arrays, the whole array, the rest of the memories are wasted. So you must estimate maximum size needed for standard arrays. Sometimes okay, but sometimes not. It just wastes memory. Or if you need more memory, you cannot allocate on that time. So these are some limitations for standard arrays, where dynamic arrays don't have that limitation. Okay, so how we can create dynamic arrays in C++? It's a very simple process. It allows us to allocate memory during the program's runtime, providing flexibility compared to standard arrays. Now we will use a new operator here. The new operator in C++ dynamically allocates memory from the heap, which allows you to create arrays where the size can be determined during the program's execution. Now, this is the example how we create the dynamic arrays. Now here double PTR is a type definition for a pointer to double. We declare D as a pointer to double, and then we use the new operator to allocate an array of 10 elements of type double. Now the size of the array is specified within the brackets, just like a standard array. So after allocation, you can treat this dynamic array just like a standard array. You can access elements using index notation like D0, D1, D3, etc. The main difference is that the size is determined at runtime and the memory is dynamically managed. Now here dynamic arrays are, as I said, it is very useful when you don't know in advance how much data you'll need to store. For example, in a scenario where the array size depends on user input or the results of a calculation, the dynamic arrays give you flexibility to allocate memory when needed. Okay, so we'll see an example here. So this example illustrates how arrays behave as constant pointers. So here we declare P as a pointer to an integer using the type definition alias integer PTR, and then we also declare an integer array A with 10 elements and an index variable for looping. So in this loop, we initialize each element of the array A with its index value. So after this loop, A will contain values from 0 to 9. Now P equal to A on line 14. Here we are assigning P to point to the same memory address as A. Since A is a constant pointer to its first element, this assignment is legal, as we saw before, meaning P now points to the first element of A. So on this loop, we print the values pointed to by P, which are the same as the values in A because P points to the same location as A. The output will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then on the next for loop, here we increment each element pointed to by P by 1. Since P points to the same memory as A, the values in A are also updated. Now it will show 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then finally we will print the values of A again. Since we modified the values through P, the new output will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you see here the output. So now if you look at here, the first one is 0 to 9 and the second one is 1 to 10. Now let's see another example here. So here we have two function prototypes, fill array and search. Then we have main function. Inside the main function, the program first asks the user for the size of the array, which is stored in array size. Then dynamically allocate an array of integer of size array size using the new operator. This array is stored in A, which is a pointer to integer. So after that, the fill array function is called to populate the array with values. So the user is prompted to enter a target value to search for in the array. The search function is called to find the target value's location in the array. The result and index is stored in the location. Now the program checks whether the search was successful. If location is equal to -1, it means the target value wasn't found in the array. Otherwise, the target value was found at index location. Then after the searching, the dynamically allocate memory is freed using delete destructor delete A to prevent memory leaks. Now these are the two functions, fill array and search. You can just look at those functions. The body inside the functions, what they're just doing is just printing enter the size, integers, and then it's just storing, and then here it is just searching using a while loop, and then if condition. And now this is the output. So first of all, it will say this program searches a list of numbers. Then it will say how many numbers will be on the list. It will ask you for an input. So now I just enter 8. Then it will say enter 8 integers. Now I will enter 8 integers one by one. After I will enter 8 integer, it will say enter a value to search for. So it saved all these 8 integers first, and then it will ask you to search for. So I pressed 443, so which is the 7th value. Now 7th value means 6th element. So 443 is element 6 in the array, because arrays start from 0. So if it start from 0, it is on the 6th element. Okay, so lastly in this lecture we will also see multidimensional dynamic arrays. Here if you see, so you can dynamically allocate these arrays. So first of all, in C++, multidimensional arrays are essentially arrays of arrays. You can dynamically allocate these arrays, giving you even more flexibility with memory and array size. So if you look at this code, type definition integer star integer array ptr, this line indicates that integer array ptr as a pointer to an integer. Using this type def helps simplify the syntax, especially when dealing with multiple layers of pointers. Then the next line, which declares m as a pointer to an array of integer pointers. The new integer array pointer 3, this part dynamically allocates an array of 3 pointers which will point to rows in a 2D array. Now if you have so if you look at this for loop, this loop iterates through each element of the array m. For each element mi, it allocates an array of 4 integers. So after this loop you have 3 arrays, each containing 4 integers. In total you now have a 3x4 dynamic array. So you end up with a 3x4 dynamic array where each row has 4 elements, and the array can be accessed as m row column. So why we need to use multidimensional array? So in applications like scientific computing or graphics, where data structure like matrix or grids are commonly used, we can use multidimensional array there. So we'll see an example here. So this is the example for multidimensional array. You can go through the example. This is the code and this is the output. So if you see, it's the same thing we did for normal dynamic array. It will say enter the row and column first. You will enter 3 and 4. You want 3 rows and 4 columns. Then it will say enter 3 rows of 4 integers. Now you will enter 3 rows of 4 integer one by one, and then it will say echoing the two-dimensional array. It will just give you the overview and the design of your two-dimensional array with 3 rows and 4 column.